We're going to talk about implicit differentiation today. And so when we talk about implicit differentiation, we're going to find a way to differentiate what's called a relation or an equation that's not written as a single function of x. Like if we look at this equation that's written here, x cubed plus y cubed minus 9xy equals 0, the graph of this clearly shows that this equation is not a function. Would you guys agree? Based on just the the vertical line test that you learned about at some point?
Yeah.
Right, it doesn't pass the vertical line test. This is not a function, but we still might be interested in a number of things, like where does it have a horizontal tangent line, or where does it have a vertical tangent line, or we might want the tangent line to this equation at any given x value. So we still need to be able to find a way to find the derivative of it. And so the method that we're going to use for that, when our equation is not explicitly written as y equals a function of x, is called implicit differentiation. And so the way we do that is we just differentiate both sides of the equation with respect to x. And so when we do that, we're going to end up with some little terms in there that have a dy dx attached to them, and we'll factor out the dy dx's and solve. So that may not make perfect sense yet, but it's going to make sense as we move through the day today. But these are the steps you're going to want to follow anytime you need to use implicit differentiation. So, and we're going to take a look at some of the graphs of the functions that we're dealing, or not functions, but the equations that we're dealing with today, because a lot of these implicitly defined equations look pretty cool. So like, for example, this one, x cubed plus y cubed minus 9xy gives us this nice little loop in it. This is this particular graph is called the folium of Descartes. You're all familiar with René Descartes, right? René Descartes, famous French philosopher and mathematician. Aren't you familiar with René? Yeah, you should be. Why are you familiar with René Descartes? There's two reasons that you might be familiar with him, is my guess.
He made the coordinate plane.
He what?
Didn't he make the coordinate plane?
Yeah, it's called the Cartesian coordinate system, right? It's named after René Descartes. That's one reason that you should be familiar with him. Anybody have the other reason why you should be familiar with him?
History class.
History class. Yeah, there we go. Yeah, you learned about him in history class, maybe, with any luck. You guys all know the great joke about René Descartes, right?
No.
Oh, you don't know the joke about René Descartes? Oh, how sad. I'm going to have to tell you the joke about René Descartes. See, are you guys ready? It's really good. You're going to really appreciate this.
All right.
Okay, here we go. So, one day, René Descartes, famous French philosopher and mathematician, walked into a restaurant and sat down at a table. The waiter came up to him and said, "Oh, hello. What would you like to have for lunch today?" And he ordered a sandwich. And the waiter said, "Would you like something to drink with that?" And René Descartes said, "I think not." And then he disappeared. Wasn't that a good joke?
How did he disappear? No, not really.
What do you mean, not really? It's because you don't get the joke. That's the problem. Who gets the joke? Anybody get the joke?
Nope.
No. You are all disappointments to me. Oh well. René Descartes, famous French philosopher and mathematician, is famous for saying, "I think, therefore I am." And so when he said, "I think not," about having something to drink with his lunch, he wasn't thinking, therefore he ceased to exist and disappeared. If only you knew your famous quotes by René Descartes, famous French philosopher and mathematician, then you would have understood the joke. Perhaps if you had been more learned, but you were not. And thus I am disappointed in all of you.
So what about implicit differentiation?
Wow, ouch. Don't even want to talk about my great joke. Let's find the derivative of this. Y squared equals x. Now, our original thing on the last page said take the derivative with respect to x of both sides of this. So I'm just going to write that. The derivative with respect to x of y squared and the derivative with respect to x of x. What's the derivative with respect to x of x?
X.
It's what?
1.
1.
1. Okay, yeah, okay. It's 1, right? But what about the derivative with respect to x of y squared?
2y.
So that's the derivative with respect to y, right?
Oh.
But not the derivative with respect to x. We haven't ever tried to take the derivative with respect to x of something that's not in terms of x. Right? So we have to figure out a good way to do that. And the way that we do that is we take the derivative of whatever's inside of here with respect to whatever that variable is. So we're going to take the derivative of this with respect to y. But then what do we need to multiply that by?
X.
Derivative of x.
The derivative of y with respect to x. So what we're going to do is we're going to take the derivative with respect to y of y squared, and then we're going to multiply that by the derivative of y with respect to x. What rule is that?
Looks kind of like composite to me.
It does. That's exactly what it is. We've basically treated this like it was a composite function, and we've used the chain rule. We took the derivative of it with respect to y, and then we multiplied it by the derivative of y with respect to x. It's just like dy dx equals dy du times du dx. It's just that same idea, except we didn't really specifically write it as the composite function. We took the derivative of it in terms of its own variable, and then multiplied it by the derivative of y in the variable we're interested in. And so anytime we try to take the derivative of a y term, but we're doing it with respect to x, we will always attach to it this dy dx term. Okay? So the left-hand side of this, the derivative with respect to y of y squared should be 2y, and then the derivative of y with respect to x is dy dx. So we should get 2y dy dx equals 1, or dy dx equals 1 over 2y. And that is our derivative with respect to x, or that's our dy dx if y squared equals x. Any questions on that? Everybody okay with that?
Did you get the dy, the derivative of y squared with respect to y?
How did I get that?
Yeah.
Yeah, so that's basically the chain rule. So what we're going to say, we could write it out as something like, let's say that u is equal to y. Let's try this way. Let's say that our function is z equals y squared, and we want to find dz dx. Okay, dz dx should be equal to dz dy times dy dx. True? According to the chain rule. And so that's what we've done here, is we've said the thing we're trying to differentiate is z equals y squared. So to find its derivative, dz dx, the derivative of this thing with respect to x, it should be the derivative of it with respect to y times the derivative of y with respect to x. And so that's effectively what we've done here, is we've taken the derivative with respect to y of y squared and multiplied it by the derivative with respect to y of x.
Okay.
Is that good or no?
Yeah.
Okay. Yeah, and so you're going to see this pattern will just repeat over and over and over and over again. This is the same thing. Every time you take the derivative of y with respect to x, you get a dy dx term. And it's just us extending out the chain rule through some extra variables. And we'll note that our derivative is definitely in a different form than what it's been in the past, right? Because our derivative now has y terms in it rather than x terms in it. And that's okay. It may have both x and y terms in it, and we'll see plenty today that have both. So let's do another one. This one I think should be pretty straightforward also, I hope. If we want to take the derivative of both sides with respect to x, what does the left-hand side become? The y squared should become what?
2y.
2y times
The derivative of y with respect to x.
2y dy dx, because we're taking the derivative with respect to x of y squared, which should give us 2y dy dx. And then if we take the derivative with respect to x of x minus 1 over x plus 1, what rule should we use for that?
Quotient.
Quotient rule. So x plus 1 times 1 minus x minus 1 times 1 over x plus 1 squared. And what will we do with this 2y? We can divide both sides by 2y, and we'll end up with a 2y times an x plus 1 squared in the denominator. And up here we've got x minus the x will cancel out, and we've got a 1 minus a negative 1, which should become a 2. And so we should, in the end up with dy dx equals 1 over y times x plus 1 squared. And now our derivative's got both x and y in it, and that's fine also. Any questions or issues with that?
So these are still derivatives, so these equations would still find you the slope of the tangent line to the equation.
That is
Or is it-
100% correct. Yep. So let's take a look at what this graph looks like real quick. Let's pull it up on Desmos here. So we had y squared. Was it x plus 1 over x minus 1, or the other way around?
I don't see Desmos.
Desmos isn't open.
Sorry.
It's x
Was
minus
it-
1 over x plus 1.
X minus 1 over x plus 1. Okay. So this is what this graph looks like. Clearly not a function. Lots of places where it doesn't pass that vertical line test. Let's see. Let's find a point on here, like the point x equals 1, y equals 0. It's already showing that one for us, right? X equals 1, y equals 0 is on there. So if we go back here and we're going to say x equals 1, y equals 0. We could check and make sure that's true. But if x is 1, we get 0 over 2. And if y is 0, we get 0. So that's true. So if we went in here and tried to plug in x equals 1 and y equals 0, if we were to evaluate it at that point, we'd end up with 1 over 0 times 1 plus 1 squared, or we'd end up with something that was undefined, right? And if we look back at our graph, the slope of the tangent line at the point 1, 0 should be undefined, right? It's a vertical tangent line there. Everybody see that?
Yep.
And if we picked some other point, that we knew was on there, I mean, there's none that are popping up here that are real nice. I don't really feel like solving for one, but we'd see that it would work out still. And we'll do some of that later today. Everybody good so far with that or no? All right, let's take a look at the next one. So we've got x equals tangent y. You guys want to see if you can differentiate that one on your own real quick?
Yeah.
All right, give it a shot. So on the left-hand side, what did you guys get?
Secant squared y
I got
times
one.
the derivative of y with respect.
Yeah. On the left, I got 1, but on the right, yeah, secant squared y times dy dx. Yeah? Everybody good there? Yeah.
Yeah.
And if we divide by secant squared y, that gives us 1 over secant squared y, or just what?
Sine squared.
1 over secant should be
Cosine
cosine, right? So cosine squared y equals dy dx. So real quick, we'll take a look at the graph just for fun. What should x equals tangent y look like? Should just look like a tangent curve that's been flipped on its side, right? This is just the inverse tangent function, isn't it? X equals tangent y. If you take the tangent of both sides, you get, or sorry, if you take the inverse tangent of both sides, you get y equals inverse tangent of x, right? This is the inverse tangent equation, except without any restrictions on its range. Let's suppose we looked at the point 0, 0. Well, actually, let's look at the point 0, pi. Right, that's a good point, yeah, 0, pi. That's clearly on the graph.
Yeah.
So we're thinking about x equals 0, y equals pi. And if we were to plug that into our derivative, well, what's cosine squared of pi? What's the cosine of pi?
Negative 1 squared.
Negative 1, so we square that gives us 1. And so we know that the equation of the line tangent here should be y minus pi equals 1 times x minus 0, or y minus pi equals x. And so we can see that this still does exactly what we wanted to do. Y minus pi equals x, and there is our line. And it's tangent to the graph there. It doesn't quite look like it because our graph has a change in concavity there. So we are tangent at that specific point, though. It doesn't quite look like it, but it is. Suppose we picked another good point on here. What's another point that we know should fit here?
Two pi, 0, 2 pi.
Well, let's pick one that's off of the y-axis. It's not on the y-axis. So let's pick, let's say y equals pi over 4. How about that? If y equals pi over 4, then what does x equal?
Square root 2 over 2.
Tangent of pi over 4 should be what? Not 2 over 2, that's sine or cosine of pi over 4.
Oh yeah, wait, sorry, 1.
Should be 1, right? So this is the point 1 comma pi over 4. And if we were to plug in pi over 4 as our y value into here, then cosine of pi over 4 is root 2 over 2. Right, we'll say dy dx at y equals pi over 4 gives us root 2 over 2 squared, or 2/4 or a half. So what would that equation be? That one would be y minus pi over 4 equals 1/2 times x minus 1. And I think this will give us a little bit better illustration of that tangent line, because the one we picked initially wasn't super great. Y minus pi over 4 equals, what was it, 1/2 times x minus 1. And we can see right there that at that point, 1 comma pi over 4, we're tangent to our graph, still a tangent line. Everybody good with that? See that this still works even though it's an implicitly defined equation?
Yep.
All right, cool. All right, let's do another one. X squared y plus xy squared equals 6. Before we get started on taking the actual derivative of it, let's take a look at what the graph is, yeah? So x squared y plus xy squared equals 6. I get that typed in right? Yeah, x squared y plus xy squared equals 6. So again, one that's clearly not a function, clearly can't be defined solely as just y equals something. Right? And I was going to say that might be a nice point there, but it doesn't appear to be a nice point that we can check. Maybe we'll figure out what that is later. Everybody good with the graph? Let's try to find this derivative. So we're taking the derivative with respect to x of x squared y plus xy squared. To start with, let's do just the x squared y part. What do we have to do to take the derivative of x squared y? Just this piece of it.
Should we use the product rule?
We need to use the product rule. Exactly. We have to use the product rule because we have two different functions that we're multiplying together. One of them is x squared, and the other one is y. And we're taking the derivative of this with respect to x. So we should get x squared, and then the derivative of y. Well, what's the derivative of y with respect to x?
1.
It's 1
Or
times
that dy
one
dx.
times
times.
dy dx, exactly. So the first half of the product rule should be x squared dy dx. And then the second half of the product rule should be plus the derivative of x squared is
2x.
2x.
2x. And then the y just stays as a y. Since I didn't take the derivative of the y term on the second part of the product rule, I don't put a dy dx next to it, right? Because it's just the derivative of x squared times y. Everybody good with that?
Yeah.
Now what about xy squared? What are we gonna have to use?
Same one.
Product rule. And big mistake that a lot of people make is they don't use the product rule for these in implicit differentiation. You need to use the product rule. So plus, this time it's going to be x, and then times the derivative of y squared with respect to x. So what is that derivative?
2y times dy dx.
2y times dy dx. We get the dy dx because we're taking the derivative of a y term with respect to x. And then plus what? This time the y squared should stay, and we're multiplying it by the derivative of x, which is just 1. Everybody good with that? Equals what?
0.
0.
0, right. Other common mistake people make with this is they forget to take the derivative of the right-hand side, especially when it's just a constant. So if it's constant, make sure it turns into a 0. All right, so now we're looking for dy dx, which means that we need to solve for that dy dx. We need to factor out a dy dx from these two terms. Right, this one has a dy dx and this one has a dy dx. And everything else needs to get moved to the other side. So we're going to have x squared dy dx plus 2xy dy dx equals negative y squared minus 2xy. Everybody good with that?
Yep.
Okay, and then we will factor out the dy dx on the left. And divide by that x squared plus 2xy. So we end up with dy dx equals negative y squared minus 2xy all over x squared plus 2xy. Any questions on that derivative of x squared y plus xy squared equals 6?
What happened to the 6?
So remember, we're taking the derivative of both sides of this. So the derivative of a constant is 0. That's draw the arrow here. That's the derivative of a constant is always 0. Any other questions on that? And we won't bother to find a point that works for this to plug it in and draw the tangent line, but we'll figure that out another time with some other ones. All right, why don't you guys see if you can figure out this one on your own? So take 2 or 3 minutes and try and find the slope of the circle, x squared plus y squared equals 25 at the point 3, negative 4. How'd that go? Did you guys finish that up?
Yeah.
All right. So first off, you should have got 2x plus 2y dy dx equals what?
0.
0?
0.
Okay. Everybody get that as the beginning step for their derivative.
Yes. Yep.
Okay. So we should have got dy dx equals negative 2x. Let's subtract that over. Divided by the 2y. And then we can cancel out the 2's to get negative x over y. Everybody good there?
Yes.
We'll evaluate that at the point 3, comma, negative 4, which gave us what?
Three-fourths.
Positive 3/4. That's the slope of our tangent line, or the slope of the circle. If we wanted to write the actual equation of the tangent line, it would be y minus negative 4 equals 3/4 times x minus 3. I didn't ask you guys to do that, but that's what you would have gotten. And if we were to graph it, we should be able to see that that is the tangent line. So y minus -4, and then 3/4 x minus 3. Yeah, everybody see that? There's your circle, there's your tangent line at the point 3, -4. Everybody good?
So in our answer, like, could we do like the slope of the tangent line equals 3/4? Would that be like our?
Yeah, I mean that's what I mean the slope of the circle, the slope of the function is the slope of the tangent line.
Okay.
So yeah. All right, next problem. Let's show that the slope is defined at every point on the graph of 2y equals x plus sine y. So to take the derivative of 2y equals x plus sine y, first we'll do the left-hand side. The derivative of 2y should be what?
Two times dy dx.
Yeah, 2 times dy dx. And what about the derivative of, that's just an x, right? The video, the meeting control, that's x squared. Okay. So the derivative of the x squared is 2x. And what about the derivative of the sine y?
Cosine y dy dx.
Cosine y dy dx. Everybody good with that?
Yeah.
Yep.
So if we solve for dy dx, we'll have to bring that cosine y dy dx to this side. And as we factor out the dy dx, we end up with 2x over 2 minus cosine y. Everybody good with that? Hopefully. Yeah. All right. Now then the question is, show that the slope is defined at every point. Well, can I plug in any number for x?
Yeah.
Yep. And what about for y? Well, I can't have the denominator of this equals 0, right? So we'd have to say that 2 minus cosine y can't be equal to 0, which would tell us that 2 can't equal cosine y. So anytime that the cosine of y equals 2 would be a place where this is undefined, right?
Yeah.
When does cosine y equal 2?
Never.
Right. Yeah. Cosine y never equals 2 because the range of cosine is -1 to 1. So therefore, there are no values that make this. Just for fun, because some of these are cool looking, let's take a look at the graph. We got 2y equals x squared plus sine y. Yep, this one's not very cool looking. Tries to be a parabola, but it's got like these weird little oscillations to it. I guess maybe it's cool. I don't know. But that's what the graph of that looks like, and we should be able to find slopes of tangent lines at any points that we could define on it if we wanted to. Any questions, or everybody good with that one?
I have a quick question. So when we're doing implicit differentiation, like when do we do it? When we're looking at a function, how do we determine if we want to do implicit differentiation versus use other rules like that will help us solve it? Is it only when it's not a function, or is there?
Right. So when it's not a function,
do it on anything. Or?
Basically, if we've got x and y variables in there that can't be separated, so if we can't write the function solely as y equals something all in terms of x, then you're going to have to use implicit differentiation.
So on this one, if we just wanted to divide both sides by 2 and like use other stuff, could we do that? Or would you recommend implicit differentiation because it's a lot easier? Or?
No, you can't just do that, because if we do that, we've got x squared plus sine y over 2. It's not written as y equals a function in terms of x. It's written as y equals some other stuff with also with a y in it. If that was x squared, if that was 2y equals x squared plus sine x, then sure, divide by 2 and take the derivative like you normally would. But since it's got a y over there, then you can't. If it's got y's on both sides, or even if there's just y's on one side, but it's like, you know, a y cubed plus y squared minus y is equal to some stuff with x's, then you're still going to need to use implicit, because you can't solve that directly for y. Does that make sense?
Okay. Yeah.
Okay. Cool. Good question, though. All right, here we've got a nice figure 8 curve. Y to the 4th equals 9y squared minus 9x squared. And we want to write the equation of the tangent line to this at the point 2 root 5 over 3, comma 2. So we'll see, this is a good one for implicit differentiation. 1, because we know it's not a function. And 2, because it's got y's on the left and y's on the right. So what should we do to take the derivative? Left-hand side should become what?
4y cubed dy dx.
Good. And the right-hand side should become what?
18y dy dx minus 18x.
Exactly. And then what should we do?
We can move the 18y dy dx to the left side and then factor out a dy dx.
All right, I'm going to do both of those in one step, if that's all right. So I brought the 18y dy dx over and factored out the dy dx from both of them. And we end up with dy dx equals negative 18x over that 4y cubed minus 18y. And we want to evaluate this at what point? 2 root 5 over 3, comma 2. So what does that give us? In the numerator, we got negative 18 times 2 root 5 over 3. And in the denominator, if we plug in 2, we got 2 cubed is 8 times the 4 is 32 minus 36. So first off, this is a negative 18 over 3, which is going to be a negative 6. And we got a negative 6 times the 2, so that's negative 12 root 5 over negative 4. So what do we end up with? I did all my
3 root 5.
Right? 3 root 5. Good. And so we don't quite have the room here to write it, but we should end up with y minus 2 equals 3 root 5 times, what was it, x minus, what was it, 2 root 5 over 3?
2 root 5 over 3.
Cool. And if we go in and look on Desmos, let's see, we started off with y to the 4th. All right, y to the 4th. What was the original equation? Y to the 4th equals
9y squared minus 9x squared.
9x squared. Okay, cool. There's our figure 8. And we ended up with y minus 2 equals 3 root 5 times x minus 2 root 5 over 3. And while our tangent line does cross through down here a couple more times at this specific point, that point 2 root 5 over 3 comma 2, we can see that it's tangent to it. Everybody good with that? I don't care about that 0.1, 0.5. I don't know why that's on there. But everybody good with that?
Yep.
Cool. All right. We're going to talk very briefly about this term called orthogonal. It's not part of what you need to know for the AP test. They don't normally talk about things being orthogonal. But as you get into higher math classes, it's a concept that pops up fairly often, especially when you start doing stuff in 3 dimensions. So the term orthogonal, when we refer to curves being orthogonal, it means that they share a point and that the tangent lines at that point are perpendicular. Okay. So we want to try to prove that these two equations are orthogonal at the points 1, 1 and 1, negative 1. So how will we go about doing that?
Do the derivatives of both equations to find the tangent lines?
Derivatives of both of them to find the tangent lines, and we got to do both of them implicitly. So this first one should be 4x plus 6y dy dx equals 0, and the second one should be 2y dy dx equals 3x squared. Everybody good with that?
Yep.
All right. Then we simplify dy dx on the right here. The one in blue should be 3x squared over 2y. And on the right-hand side, dy dx should be negative 4x over 6y or negative 2x over 3y. Good or no?
Yeah.
All right. And then what do we need to do?
Plug in the points.
Yep, just plug it in. So plug in 1, 1 gives us what? Let's see, 1, 1, this equals negative 2/3. And at 1, negative 1, what does it give us? Should be positive 2/3. And for this one at 1, 1, this should equal 3/2. And at 1, negative 1, we should end up with negative 3/2. And so at the points that they share, 1, 1 and 1, negative 1, they have slopes that are opposite reciprocals. Therefore, we can say that these two curves are orthogonal to each other at those points. Good or no?
Good.
All right, cool. Let's keep moving then. Let's see if we can find, oh, that's really small. Find the equations of all of the vertical tangent lines to this equation here. What are we going to do to start that? Should just need to take a derivative, right? We're looking for vertical tangent lines. That's going to be places where our derivative is undefined. So we'll start with the derivative. 2 minus 3 dy dx on the left. Good or no? Okay. And on the right, 2x minus 3y squared dy dx.
Yep.
Good or good? Yeah, everybody good there? Okay. And then let's simplify this all down. Let's bring the 3y squared to the left and this 2 to the right. So we'll end up with 3y squared minus 3 times the dy dx equals 2x minus 2. Everybody good there? And then we divide by 3y squared minus 3. Everybody happy with that derivative?
Yes.
All right. So then what do we want to know? We want to know when this tangent line is vertical. And so if the tangent line is vertical, that means that the derivative is undefined. And if the derivative is undefined, that means that the denominator would equal 0. And if the denominator equals 0, we can set it equal to 0. 3y squared minus 3 equals 0. And that gives us y equals what?
Plus or minus 1.
Plus or minus 1. So at y equals 1 and y equals -1, we should have vertical tangent lines. But are those the equations of the vertical tangent lines? Those are not equations of vertical lines, right? Those would be equations of horizontal lines if we use those. So how do we find the appropriate x value for the vertical tangent line?
Do we plug it back in?
Yep, we got to plug it back into our original equation. So if y equals +1, we'll have 2x minus 3 equals x squared minus 1. And we should be able to solve that. It's just a quadratic, right? X squared minus 2x, and then we'll add the 3 over here. So x squared minus 2x plus 2 equals 0. And we can either complete the square or we can use the quadratic formula. And what happens if we do that? What happens if we try to solve this quadratic?
I got a negative under square root.
Exactly. So this has no real solutions. All right, so let's try -1. Plug in -1 for y, we end up with 2x plus 3 equals x squared, and then that should become a +1. Yeah, and that gives us x squared minus 2x, and then minus 2 equals 0. And for that one, we should be able to get some solutions, I think. Quadratic formula or completing the square, either way should work. We'll use quadratic formula. Gives us x equals 2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times -2, so 4 minus -8, or 4 plus 8, all over 2. And if we simplify that down, this becomes 2 plus or minus root 12 is 2 root 3 over 2, or x equals 1 plus or minus root 3. Everybody good with that?
Yep.
Yeah.
All right, so let's take a look in Desmos. What do we have? We had 2x minus 3y, I think, equals, what was it, x squared plus y cubed or something? I don't even remember. X squared minus y cubed? Is that right?
Yes.
Yeah.
And so this is that graph. It's not an ellipse, but some sort of like ellipsoid looking thing down here, and this other weird little V-shaped graph up above. And we got x equals 1 plus root 3 and we got x equals 1 minus root 3. And amazingly enough, there's our tangent lines there and right there. And we'll see that the y values are -1 for both of them, right? And then our x values are 1 plus or minus root 3. And they're tangent to the graph at this specific point. They may go through it somewhere else, like up here, for example, at 2, but still tangent at this point. Everybody good?
Yeah.
All right, let's do another one. This time we're going to look for horizontal and vertical tangent lines. You guys want to see if you can work this one through on your own?
Yeah.
Okay. This one's probably going to take us a little bit of time. This may be all we get through today. So take 4 or 5 minutes and try and get through this. It'll take a bit of time. How are we doing with this one? Getting along all right? Anybody have any questions as you're working through it?
Yeah, I have a question. So I got the derivative, and I'm kind of stuck at that point.
Okay, so let's start here. We got hopefully you got 4x minus 12y squared dy dx to start on the left, and 3x squared minus 2y dy dx on the right. Everybody
Yeah.
good with that first step? Okay, cool. And then when you rearranged, you should have got 4x minus 3x squared on the right. Sorry, on the left. I know my left from right, I assure you. And 12y squared minus 2y times the dy dx. And so your derivative should have been 4x minus 3x squared over 12y squared minus 2y. Yeah?
Yeah.
All right. Everybody good to that point? Let's just work through it from there together. So, I'm not sure who was asking me this question, but you got stuck with the find the actual equations, the horizontal and vertical tangent lines. Is that right?
Yeah.
Okay, so let's start with horizontal. If we want horizontal tangent lines, that means that the numerator needs to equal 0, right? That's how we'd get a horizontal tangent line. Are you good with that? If the numerator equals 0, then that whole derivative equals 0. And if the derivative equals 0, then it's horizontal. Okay. So we got 4x minus 3x squared equals 0. We can factor an x out of that. So 4 minus 3x equals 0. And so one place where this occurs is at x equals 0. And another place is at x equals 4/3. Good with that or no?
Yeah.
Okay. So then what we need to do is we need to plug x equals 0 back into this original equation to find the y value, because we're looking for a horizontal tangent line. And that's a y equals equation. So if x equals 0, we've got negative 4y cubed equals negative y squared. Everybody good with that?
Yep.
Okay. And then we'll solve this to get we'll say 4y cubed minus y squared equals 0. And we'll say that that gives us y equals, we'll factor out the y squared times 4y minus 1 equals 0, and y equals 0, and y equals 1/4. So far, good with that?
Yeah.
Okay.
Yeah.
Cool. So we're gonna come back to that in just a second. Let's do the vertical tangent lines, because there's a little bit more we got to unpack with that. There's a little more to deal with. So let's do the vertical tangent lines. We want the denominator to equal 0 for a vertical tangent line. So that'll be 12y squared minus 2y equals 0. Or that would occur if we take out the 2y times 6y minus 1. So that would be at y equals 0 and at y equals 1/6. True?
Yeah.
All right, cool. So we still got, remember, we're still got to do the x equals 4/3 part on that top one too. Didn't get around to that yet, but we'll do that too. Let's just plug in the y equals 0 here. If we plug in y equals 0, we end up with 2x squared equals x cubed. And what do we get for that? We end up with x equals
cubed.
That's right, yeah,
X
we'll
cubed
write
minus 2x squared.
Yep, and so x squared times x minus 2 equals 0, and x equals 0, x equals 2. So one of the points that we're talking about here is the point when x equals 0, y equals 0. True? Right,
Yeah.
x equals 0, y equals 0, and over here the same thing, x equals 0, y equals 0. And if we plug in x equals 0 and y equals 0, we get 0 equals 0. True. So there should be a point on our graph at x equals 0, y equals 0. But at that point, if x equals 0 and y equals 0, what happens to our derivative?
It's undefined or indeterminate.
It's indeterminate, right? And we got to make that important distinction that if x equals 0 and y equals 0, so I'm going to give us a new page here. If x equals 0 and y equals 0, then dy dx is indeterminate. And if dy dx is indeterminate, then there is no tangent line at that point. It's just simply a point on the graph because it worked on the graph, but it's not actually got a tangent line there. It's just some separate point that's just separate from the entire rest of the graph. And so I'm real quickly then going to go in here and graph this original function that we were dealing with, which was what, 2x squared minus 4y cubed equals x cubed minus y squared. And we'll see it doesn't look like anything is happening here at the point 0, 0. And Desmos has difficulty plotting just a single point that's part of a graph. So it's got the whole smooth curve part of it here that we've got, but it doesn't show that point at 0, 0. And there's no tangent line at 0, 0 because it's simply just a point there. Does that make sense? Hopefully. So it's very important that when you're doing these implicitly defined ones, especially, that if the same value, the same point, x equals 0, y equals 0, gives you an indeterminate value for your derivative, there's no tangent line there. Good or no?
Yeah.
Okay. So now we'll go in and say, well, we did this with x equals 0 and got y equals 1/4. And so if we go back to our graph at y equals 1/4, we should see, if we zoom in on that a bit, we are tangent to our graph there, y equals 1/4. And then the other one that we got was at x equals 2, I believe. Is that right? So we should be able to see one there at x equals 2 if we zoom in a little, right, where that's a vertical tangent line. Everybody see that one?
Yeah.
Cool. And so then all that's left is some fairly unpleasant arithmetic on our other values. So we'll go through, we still need to do x equals 4/3, and we still need to do y equals 1/6. So at x equals 4/3, what does that give us? 4/3 squared is 16/9 times 2 is 32/9. So we got 32/9, and then what do we have? We got minus 4y cubed, and then we got x cubed, so 4/3 cubed is 64/27 minus y squared. And as we go through, we're going to find that one's really fairly difficult to solve for y. 4y cubed minus y squared. If I bring the 4y cubed over there, and 64/27 minus 32/9 is 64 minus 96, which is minus 32/27. And that's a cubic that you're not going to be able, sorry, equals 0, that you're not going to be able to solve on your own without using your graphing calculator. So if we were to go in once again to Desmos, and try to show that 4y cubed minus y, what was it, minus y squared. Actually, we're gonna have to do it with x values because otherwise it won't graph it properly. 4x cubed minus x squared, and then what was it, minus 32/27. that gives us a value of 0.761 approximately. So if we were to type in y equals 0.761 approximately, we should see that we're just slightly off, but basically that's this horizontal tangent line right up here. Everybody see that?
Yeah.
Yep. Okay, we're going to talk more about how to do that another time because we're getting close to being out of time here. In fact, we're probably like already out of time, but I like to go over anyway. It's not like it takes you long to get to your next class, right? Of course not. So about 0.761. What time are we supposed to be done? 27, right?
Yeah.
Okay, all right, so we're good. We got time. I mean, it's 11:27, but and lastly, if we plug in y equals 1/6 up here, we're going to do the same kind of thing, and we'll find the other vertical tangent line that way. We'll talk more about this next time because I know you guys do have to go. Any questions on anything we've done so far today?
This is a little unrelated, but the chain rule packet, that's due tomorrow night or today?
Mm-hmm. That's going to be due tomorrow. It says today right now, but I'm going to adjust the due date for tomorrow. And I'm going to put up a short thing with basic implicit differentiation. And in fact, that chain rule one, we didn't get through as much today as I wanted to. So that chain rule one's probably not even going to be due until Friday afternoon or Friday evening. So
Okay, thank you.
I'll redo that for Friday, and then I'll put up an implicit one, a simple implicit one for today, and then a little bit more complicated implicit one for tomorrow. And then the chain rule will be on Friday.